All right, now we're going to turn to homework help for section 6.5, number 11. And in this problem, we have a population of x's, which have a mean. Mu is 15 and standard deviation is 14. There's no statement on whether this is normal or not. We're going to start taking some samples out of here. And what we know is that if the n, the size of the sample, is large enough, then the x bars that come from these samples will be approximately normally distributed with the same mean as this population and a standard deviation that's different but related. It's this standard deviation divided by the square root of n, where n is the sample size. So we're asked three questions here. The first is this. If we take the random samples of size n equals 49, find the mean, the standard error or the standard deviation of the x bars, and the probability that x bar will land between 4 and 6. Then we're supposed to repeat that for size 64. We will get different probabilities and we'll get different standard deviations, and we're supposed to explain the effect that we see. So let's jump in here to part A. In part A, we're told that the sample size is 49. So unless there was some strong skew or outliers in this original population, it would be reasonable to think that the x bars coming from these samples of size 49 are normal because the sample size is at least 30. So we are expecting a normal distribution for x bar. And that normal distribution has a mean and a standard deviation. Normal, the mean is mu, which is 15. And the standard deviation for x bar now is the standard deviation from the original population, 14, over the square root of the sample size, which is 49. So, mu of x bar is 15. Standard deviation of x bar is 14 over root 49. Now, 7 times 7 is 49. So the square root of 49 is 7. 14 divided by 7 is 2. And so x bar is normally distributed with a mean of 15 and a standard deviation of 2. We are looking for, by the way, that takes care of those first two pieces there. Now we're looking for the probability that x bar will fall between the values of 4 on the bottom and 6 on the top. Okay, so what we need to do, by the way, this we had an error here. It's a probability that x bar lies between 15 and 17, not 4 and 6. So we've already computed the mean of x bars. That's 15, and the standard error of the x bars is 2, and that's the sigma over root n formula. So now we'd like to translate this statement to a corresponding statement about z-scores. So what we're going to do is run each of these through our z formula. Now remember, these are values of x bars. So we use that formula that we've been learning. X bar of 15 minus the mean for the x bars. And what goes down here doesn't really matter, right? We have 15 minus 15 is 0. So we get a 0 there. Let's call that Z1. Z2 is our next x bar value. The next x bar value we're interested in is 17. Subtract off the mean of the x bars, divide by, now sigma over root n we've already computed, that's a 2. So 17 minus 15 is 2, 2 over 2 is 1. So we're interested in z values between 0 and 1. Now, if we were going to do this by means of a table, the way we would do it is we would look up the probability. Well, let's just sketch a picture here before we start the calculations. So the idea is we have our normal distribution here, and standard normal distribution has a mean of 0. So we want to go between 0 and 1. We're looking for this area right here. Now, your table won't give you that, but what you could do is to compute the area that is less than 1, which would take all of this, and then subtract off the area that's less than 0, which is there, and you'd have in between this value right here. So the probability that z is less than 1 minus the probability that z is less than 0. Now, this one you actually don't have to look up. The probability that z is less than 0, well, half of the area is below 0, and half the area is above 0. So we know that one already. All you need to do is look up the area for z is less than 1. We can do that with a table, or we can do that with our calculator. So we go to the distributions, normal CDF, standard normal. We're looking at from minus infinity up to 1. We get 0.84134. And all we're doing is subtracting 5 from that first digit. 0.34134, or a little bit more than a third, is the probability that the mean would land in those limits, 15 and 17. Now, there's another way you can do this with your calculator, and I want to show that to you. So let's go back here. Probability z 0 is less than z is less than 1. This you can get directly on the calculator, and it's worth learning how to use that function. So I'm going to go right back here where I was before, the normal CDF. By the way, we'll almost never, let me back up here, we'll almost never use this first option, the normal PDF. What that's telling you is how tall that z curve is at any particular point. That's not of much interest to us. There are some things that you can do where the PDF is of interest, but that really just doesn't come up in this course. So we're going to be looking at the normal CDF. And what we want to do now, rather than use that very negative minus 1 times 10 to the 99th, what I'm going to do is just look right here and say I want the area between 0 and 1. So what I can do on my calculator is put in a 0 for the lower, a 1 for the upper. Mean and standard deviation are 0 and 1 because we're talking about z-scores. That's the standard normal. And type that in, and you get 0.34134. Well, sure enough, that's what we got before. But as a matter of fact, this actually gets even better. And that is, we were interested in this. What is the probability that the x bars lie between 15 and 17? You can do that directly on your calculator as well. The key, though, is that you must know these values before you start. We need the mean of the x bar and the standard deviation of the x bar. These you must compute every time. The calculator does not allow you to avoid knowing what those are. But once we have that, what we're interested in is this. I'm going to go to distribution, normal CDF. Now the lower, I'm going to say, is not 0 and 1. I'm going to work with x bars directly. So 15 to 17. But now my mean and standard deviation are 15 and 2. And if I run that, look at that, I get exactly the same value again, 0.34134. And so there are three ways we could do it. This is the way you would do it if you're working with a paper table. And let me emphasize, there is nothing wrong with that. If you prefer to work with a tangible table, I don't have any problem with that. And sooner or later, if you do much in statistics, you're going to come across cases where you actually need to use a table. So it's a skill worth knowing. Secondly, we could do this between the values 0 and 1 directly for the z. If you do that, you set your mean to be 0 and your standard deviation to be 1, because that's what z means. It's the normal distribution that has that mean and standard deviation. And finally, you could answer this question directly on the calculator, but that requires you to compute the mean of x bar and the standard deviation of x bar. So it's of limited utility. You still end up doing these calculations, which we used down here. You could avoid putting it in this formula, but that's not all that much help by my way of thinking anyway. So there's the first part. We have the probability of landing, x bars landing between 15 and 17 is about 34%. Now in part B, we want to repeat these calculations, but this time use a sample size of 64 rather than the earlier sample size of 49. All right, that means that we're going to need to know how x bar is distributed. Once again, we're working with sample sizes more than 30, so unless there are skew or outliers, we expect this to be normal, with a mean of mu of the original population and a standard deviation of sigma over root n. Let's get those new values. Well, changing the sample size does not affect the mean. So the mean of our original population was 15 and its standard deviation was 14. So we have a 15 in here. And the new standard deviation is going to be 14 over root n. Square root of n, square root of 64 is 8, because 8 times 8 is 64. And now our standard deviation for x bar is 1.75 rather than the earlier 2. So we've done just now the first two parts of this. List the mean for x bar, that's still 15. List the standard deviation for x bar, we just computed that, that's 1.75. And then find the probability that the x bars for samples of size 64 now land between 15 and 17. Okay, well, we have three ways of doing it. If you were working from a table, the first thing you'd want to do is translate this to z-scores. So I need z-scores above and below. z1, this lower one, is 15 minus the mean of x bar over the standard deviation of x bar, or you could say sigma over root n here. It would be the same thing. So the mean of x bar is still 15. So this is still 15 minus 15, which is 0. And we don't care what's down here. If you take 0 divided by any non-zero number, you're going to get a 0. So we get a 0 there. The upper z is looking for 17. Let's get a little more room here. 17 minus the mean of this distribution is 15. Divide by the standard deviation for this distribution, 1.75. And this is something to actually compute now. So 17 minus 15 is 2. Divided by 1.75 is 1.1429 if we round off. Okay, so 1.1429. All right, now our probability can then be computed, if we were working from a table, we would go like this. The probability that z is between 0 and, now remember, a table is going to round this off to 2 decimal places, so it would be 1.14. But I'm going to be using the calculator, so I'll keep a few more digits, and that way all my different ways of computing this will be consistent. I'd have this kind of a picture. Normal distribution, mean for z is 0, standard deviation is 1. I want to go to 1.1429, that'd be up in here somewhere, and down to 0, I'm looking for this area. And the way you do that is you find all of the area to the left of 1.1429. That'd be from here all the way back, minus the probability that z is less than 0. That'd be from here all the way back. Well, from here all the way back, that's just 1/2 of this symmetric distribution. So that's going to be 0.5 for this one. This is the only one we really need to look up. You could look this up on your table, look up 1.14, or you could do it on your calculator. So we need the probability that z, mean of 0, standard deviation of 1, is less than 1.1429 on our calculator. We'll go to the list of distributions, normal CDF. Now here you could use -1, you could times 10 to the 99th, you could use -10, it really wouldn't make any difference. The upper limit, 1.1429, we've got entered. Then the mean and standard deviation are 0 and 1. Paste those, and I get 0.87346. Of course, I need to subtract 1/2 from that, and I get 0.37346. And that is to say the probability is about 37.3%. Okay, now the last part of this question is to explain the differences between this part, where we have a sample size of 64, and this part up here, where we had a smaller sample size of 49, I think it was, yes. Sample size is 49 in this first part. So here's the situation. In the first part, if we go from 15 units to 17 units along the x bar axis, that's an increase of 2 units above the mean. Those 2 units are just 1 standard deviation here. But down here in part B, the standard deviation is smaller. So it takes more of these smaller standard deviations to get 2 units along the x-bar axis. So here we go from, on the z-axis, we go from 0 to, what is it, about 1.14, whereas up here we went from 0 up to 1. So we're going more standard deviations out here to go from the mean 15 up to the 17, and therefore we're including more of the distribution, and therefore we get a higher probability. That's the explanation.